In this video, we're going to talk about logarithmic functions. So logarithmic functions are inverse functions of exponential functions. So the inverse of an exponential function is called a logarithmic function. Again, just like the exponential function, we've got b greater than 0 and b not equal to 1, and we write y equals log base b of x is equivalent to x equals b to the y. So this is what an inverse function does. B is called the base, and when we have b equal to e, we call this the natural log. So the log base e of x is written as the natural log ln of x. Okay, there are lots of properties of logarithmic functions we need to know. So log base b of 1 is always 0. Again, what does this mean? This means b to the 0 is equal to 1, so that's always true. Log base b of b is 1. What does this mean? B to the power 1 equals b. So these are equivalent statements. Log base b of b to the x equals x. Well, again, rewriting this, that just says b to the x equals b to the x. So that's not very exciting. B to the power log base b of x equals x. So this is because they are inverse functions. We also have some other properties of logarithms. And I'll write down some of these. I won't work through all the detail. So log base b of m times n equals log base b of m plus log base b of n. So that's sort of equivalent of b to the x times b to the y is equal to b to the x plus y. Okay, what else do we have? We have log base b of m over n equals log base b of m minus log base b of n, and that's just taking a negative exponent on the second term. Log base b of m to the p equals p times log base b of m. I'll work this one out. So let's let log base b of m equal to y. So that means b to the y equals m. We need an m to the p here, so that's b to the y to the p equals m to the p, which is equivalent to b to the y p equals m to the power p. Okay, and now we go back and put these into log. So log base b of m to the power p, log base b of m to the power p is equal to y times p, which is just p times log base b of m, given where we started. So that's how we get that one. The last one is log base b of m equals log base b of n, if and only if m equals n. Some exercises. We want to evaluate log base 10 of a million. So that means, if we let that equal to y, that means 10 to the y equals a million. That's 6 zeros, so y equals 6. Log base 2 of 8, same idea. So if we let that equal to y, then 2 to the y equals 8, which means y equals 3. Natural log of e to the 12. Again, the properties allow us to take the 12 down. 12 times natural log of e. Natural log of e is simply 1, because that's e to the 1. And so that's just 12. Log base 2 of x squared equals negative 3. Okay, well, that means that x squared equals 2 to the negative 3, which is 1/8. So x equals plus or minus the square root of 1/8. Now, just a side note here, in your high school math class perhaps, this might not have been an acceptable answer because you would have had to simplify. I don't care about simplification. This is a perfectly reasonable answer. If you simplified it into something else, that would also be a perfectly reasonable answer. Log base 5 of 125 equals y. So we're trying to find y. Well, that means 5 to the y equals 125, which means that y equals 3. Natural log of x equals 1. That means that e to the 1 equals x, so x equals e. Okay, some more complicated exercises. Solve log base 2 of x equals 3 log base 2 of 32 plus log base 2 of 20 minus log base 2 of 5. What a mess. Okay, so let's work through some stuff here. Well, log base 2 of 32 is 5. So that's 3 times 5. And then I'm going to combine these. If we're taking the difference of two logs, we get to do the log of the quotient, or of the ratio. So log base 2 of 20 over 5 equals 15 times log base 2 of 4, 15 plus, sorry, plus log base 2 of 4. Log base 2 of 4 is 2, so that's 17. So log base 2 of x equals 17, which means that x equals 2 to the power 17, which is some big number. Log base 10 of x plus 6 plus log base 10 of x equals log base 10 of 5. Okay, so I'm going to combine these and maybe bring this log base 10 of 5 to the left. Well, it doesn't really matter. We'll just combine. So let's combine these. We can do that. If we're taking the sum of two logs, we multiply the things inside. So that's going to be log base 10 of x plus 6 times x equals log base 10 of 5. This can only be true if the things inside the logs are equal. So let's see, x plus 6 times x is x squared plus 6x equals 5. So that's x squared plus 6x minus 5 equals 0. I say to myself, I don't know how to solve this, so let's use the quadratic formula. Negative 6 plus or minus, so x equals negative 6 plus or minus square root of b squared, 36, minus 4ac, so plus 20. This isn't going to be very nice. All divided by 2. So that's negative 3 plus or minus, that's 56. 56 is divisible by 4, so that's going to be 2 square root 56 is going to be 14 over 2, which is negative 3 plus or minus square root of 14. All right, now let's look at this for just a second here. Square root of 14 is a bit bigger than 3, a little bit less than 4. So minus 3 plus square root of 14 is positive. The reason I'm asking this is, look, we've got these, x plus 6, and we've got an x here. We can't take a log base 10 or log base anything of a negative number, which means we can't use the negative 3 minus square root of 14. So the only possible answer here is x equals negative 3 plus the square root of 14. So that's our only solution to this problem. So you have to be a little bit careful. Here, again, we've said these things can only be equal. We've gone here, from this step to the next step. We've basically done an exponent, taken a 10 to the power both sides. And we've got to be a little bit careful here that we're always positive on both sides. Clearly this is positive. But here, x plus 6 times x could be positive because both x plus 6 and x are negative. All right, our last problem. An investment account is quoted as paying 4% interest with quarterly compounding. What is the equivalent continuously compounded interest rate? All right, so this investment account, if we put some money into this account, let's call that P, we are going to end up with quarterly compounded 1 plus 0.04 divided by 4 to the power 4t. That's how much money we'll end up with our quarterly compounding. Call that our future value. Equivalently, if we'd invested and the rate had been quoted continuously, it would be P times e to the RT. So we want to find this R. So we've got these two things equal to each other, cancel out the P's, and we've got 1.01 to the 4t equals e to the RT. Now what I like to do here, I know the natural log is the inverse of the exponential function of e to the x, so we're going to take the natural log of both sides. Natural log 1.01 to the 4t, and I'll just put extra parentheses to be careful, we know where everything is, equals natural log of e to the RT, which is equal to RT. Okay, we're almost done. If we've got a natural log of something to a power, we can bring the power in front. So we can, this side we can turn into 4t natural log of 1.01 equals RT. Our t's cancel, and we have, just switching sides, R equals 4 times natural log of 1.01. I'll bring up a calculator. 1.01 natural log times 4, and I'll just multiply that by 100 to put it as percent, 3.9801. So this rate is 3.9801%. So again, the investment account is quoted as paying 4% interest with quarterly compounding. If it had been quoted with continuously compounded interest rate, the rate would have been 3.9801. So that's how we do interest. Again, this is typical, right? Someone's going to quote you an investment with a particular interest rate. They wouldn't give you a choice. Basically, if you wanted a different interest rate, they're going to give you a different rate, or sorry, they're going to get, if you wanted a rate with a different compounding frequency, you would have to find out a different rate, right? 4% quarterly compounding is equivalent to 3.9801 with continuous compounding.